Hi, everyone. Can you hear me? I guess some of you can. Okay. Well, again, thanks for coming to class. I really appreciate it. Appreciate if you put your camera on. It's nice. Always nice looking at faces making. It's like, what? I have no idea what you're talking about. So then it gives me the I guess the notion that maybe you need to explain it again, or maybe in different words. Let's see. Any announcement I can?
The 7th homework is due tonight. Yeah, that's it.
Okay. How many people finished the lab? Everybody?
There's one more group left tomorrow.
Okay.
And then we're done. Yeah.
That's great. Yeah, I hope you enjoyed it. That's fantastic. That's phenomenal. Okay, let's see. Oh, actually, I have something to show you. So I ended up, for some reason, which I don't want to talk about, I ended up having an MR yesterday, which I thought was very interesting to actually share some of the experience with you and actually show you what the type of sequences that actually were performed. So here's yeah, can you see?
Yeah.
Okay, so first of all, so these are, each one of those are all individual sequences, or at least most of them are individual sequences. Some of them are actually processing of some of the sequences. But this is a somewhat routine brain MRI. And here's some of the things that were there. So first of all, the first thing that they collect is what's called localizers. So that just to know where things are within the scanner. Then let's see. Here's a few sequences that you may recognize. Let's see, coronal. So here's a 3D scan, T1. It's called T1 Bravo. T1 Bravo is basically a T1 weighted image that they use inversion in order to enhance the contrast between gray and white matter. Okay, so you do some preparation, so an inversion pulse at 180, and then they wait a little bit till the contrast between gray and white matter increases, and then they perform a few encodes, and then they repeat the preparation and perform more encodes. So that gives you good T1 contrast. Another one, and I'll show you all those images in a second. It's just hard to share multiple windows. Another one is axial 3D SWAN. So this is a susceptibility weighted angiography, it's called. So we talked about susceptibility weighting, right? So effectively it's similar to T2 star, except that what they do also is they kind of combine actually the phase image with the magnitude image. So remember with T2 star, you got, dephasing and loss of signal. And then there's another effect, which is, phase, like the phase will be different based on your echo time. And so what they do is kind of perform a combination of them in order to emphasize areas which have different susceptibility. This one is a T2 spin echo, but using what's called propeller. We'll talk about it some. Maybe I'll mention what propeller is, but at some other point. If I don't, please remind me. By the way, that could be another excellent project, propeller. And propeller is a kind of a radial acquisition trajectory, kind of a mixed radial and Cartesian. I'll mention it briefly. There's also, again, 3D, T2 weighted, but fluid suppressed. So fluid attenuated inversion recovery. It's called FLAIR. And I mentioned to you that, like, why we want to do this. So you do an inversion pulse, you wait till water crosses 0, and then there you do imaging. And this is a 3D sequence that uses spin echo for that. And then finally, diffusion, weighted imaging, which we didn't talk really about diffusion so much, but the idea is that if you remember, if you have spins that are diffusing, then if you put a gradient while the spins are diffusing, then the spins will accumulate non-linear phase. Like the phase will depend on where they are in space. And so if spins are moving, then the 180 is not gonna refocus them perfectly. And if they're not moving, then, or very little diffusion happens, then the signal is gonna just be the regular T2. So that's a very important sequence, but it's acquired using echoplanar imaging. If you remember what echoplanar imaging, it's a single, it's basically you read K-space in a single shot, very, very fast. And when you do that, what artifacts you may actually get, if you remember. Do you remember?
Was it in that Shep Logan Phantom with the ghosting?
Yeah, so it's not ghosting, it was shifting, right?
Shifting.
So basically the fat, because it's off resonance shifts, but even if you don't have fat and you still have off resonance, that will create a severe geometric distortion. And those geometric distortions will happen very close to the sinuses, ear canal, for example, because that's where you've got huge susceptibility problem in field homogeneities. Okay. All right, so let me just show you some images. Can you see? So this is a very typical T1 weighted brain. You see that when T1, remember T1, what's bright in T1? Short or long T1? What?
Short T1.
Yeah, short T1. So subcutaneous fat, you could see it's pretty bright. Okay, that's the white stuff that you see here. White matter has a shorter T1 than gray matter. So this is the white matter, and then you can see very nicely the gray matter has a little bit longer T1, so it looks darker. This is also emphasized using this inversion. So you have to understand that. So it's not just completely recovery, like it's recovery from inversion. And you can see how nicely the contrast between, contrast between gray and white matter, it's pretty nice, right? So it's a very nice sequence. You know, these are the eyes. The eyes inside, what they have?
Water.
Fluid, right? So fluid has a very long T1, and so the eyes are dark. Except, what is that?
The lens.
Yeah, the lens in your eye. And that's a little bit more solid, so it has actually a shorter T1, so then you can see it. Okay. Now, these are the eyes, and you know what is this?
The ocular nerve?
Hmm?
Is it the ocular nerve?
Yeah, that's the ocular nerve. And it's surrounded by,
Fat.
yeah, absolutely, by fat. That's right. So it's surrounded by fat. What is this bright spot? Oh my God. That you can actually track through the slices. See this bright spot? Oh, and now it kind of moves around. That's an artery. That's an artery. And there is actually a reason why it's very bright. And it's not just T1. So what happened to blood from arteries, where it comes from? Below. Outside of the RF excitation. And so the thing is, we knock the spins, they come back, we knock the spin. So you create T1 weighting, right? But the arterial blood didn't see all this knocking and rising, knocking and rising, just fresh magnetization is being knocked and produces very bright signal because of that. But then as you move up in the head, it's starting to get knocked more often, and then its signal is going to be reduced. So you only see this bright blood, arterial blood vessel at the bottom of the head as opposed to being on the top of the head. Fun,
Why
huh?
is that the only one that you see?
It's not the only one, actually. 1,
Oh,
2,
okay.
3, 4, you know, like these carotids, actually.
Okay.
See the carotid? Now you can track them, yeah. These two. Okay. Let's see what else we can see in this image. CSF, it's made out of pretty much free water. So yeah, very dark in T1. Okay. Now let me actually now add to that an axial T2, which is the propeller one. Let's see where I find it.
Mickey?
Yeah.
Why are there 2 rings of fat?
Don't know. I don't know anatomy that much. Maybe there's a little bit in the dura, I guess. So this is on the right is a T2, right? Weighted image. And you can kind of see the difference now, right? In the T2,
We don't see
water.
one, I don't think.
What?
We only see one head.
Oh, really? Oh, interesting. So maybe I'll share the entire window. It's a zoom thing.
Yeah.
Okay. So on the right-hand side, you can see a T2 side by side next to a T1. And you can see those differences. First of all, white matter now is darker because it has a shorter T2 than gray matter, which has a longer. What about the white stuff over here? Or this?
CSF.
That's cerebral spinal fluid, CSF, so free water. So it has a very long T2, so it's pretty bright, right? So yeah, this is a nice T2. Oh, and the eyes. Okay, so the eyes, of course, now are bright because they're made out of water. And then let's see, fat is a little bit darker, if you can see, than here. Again, based on T2. Okay, so this was T2. Now I want to show you actually the T2 weighted with flare, so fluid attenuated inversion recovery. So I'll do that. Axial T2 flare. There you go. Don't know why they're not the same size, but let me make it. So here's some of the differences. So this is on the right-hand side, it's still T2. So in that sense, white matter is still darker than gray matter. See that gray matter is bright, white matter is darker, but then fluid is completely gone, right? So that allows you to see a lot more things because now CSF is not an issue. This is a really, I mean, it's really useful sequence, by the way. And the right-hand one is actually a 3D sequence. So you see there's way more slices. It's much higher resolution than the left one, which, you know, only once in a few refresh start showing up, you know. You can also actually see this if I reformat. So here's a reformat to a sagittal, and this is a reformat to a sagittal. So you can see that those are, it's not isotropic resolution, the left one's very, very thick slices. But on the right hand one, I can actually reformat it as I like. Okay, so one of the advantage of 3D sequences. So this is Flare. And Flare is a really, really nice sequence. Now let me pick up the Bravo again. Okay, and now I'm going to show you the 3D susceptibility weighted. Okay, and this is how it looks. Actually, let me do annotation, basic annotation. So here you can also see the TE, the TR, the TE, and the TR. So if you actually see for the left one, the TR is very short. The TE is extremely short too. Okay. TR short, it's supposed to help with, T1 weighting. And on the right-hand side, the TE is very long. That's supposed to help with susceptibility weighting, right? Like you want to wait till T2 star has evolved significantly. Okay. And this is kind of how it looks. It's actually a combination of the magnitude image and the phase. But the way that people actually process it, they look at it slightly different. So they actually do a minimum intensity projection across a few slices. So I can actually do that for you. Here's the minimum intensity projection across 9 slices, and now you can see the veins. So it emphasizes basically what is the minimum value across a few slices. And because of T2 star decay, the veins, remember, have deoxygenated blood more. And so they have a susceptibility difference. Their T2 star is shorter, and therefore you could see the veins very nicely on this. See how beautiful? And so this is used to, for example, detect microbleeds. So when you have microbleeds, you have deposit of hemoglobin, which would pretty much result in large susceptibility artifacts. What's going on here?
That's the head of the ventricle, right?
Well, you can see on the left what you see, and here it's kind of black. Right? But what is that? It's kind of the nose, the nose pathway. So air tissue interface would result in large susceptibility and hence signal dropouts along these areas, right? Like you can't see even the eyes very well because of, let's see, you see the eyes it's very hard to see them because of susceptibility. Pretty cool, huh? Yeah. Okay, next one, I want to show you diffusion. So the diffusion one is pretty cool because it is EPI, it's a spin echo EPI. And so this is the image on the right. First of all, a lot of the signal, so diffusion is really a negative contrast. So basically the contrast, the more diffusion you have, the more decay you have. So there's a lot of diffusion, by the way, in the ventricles in the CSF because it's free water. So they usually have no signal whatsoever. And let's see. Oh yeah, so this is actually the interesting part that I want to show you. Look at the head. What do you notice on the right-hand side compared to the left? Look at how far it reaches. Like you see the distortion? There's significant distortion going on here. Like that lobe over here, it looks so nice. You know, it kind of, blobs, and like you have this elongated part of the head. And that's again because of geometric distortion due to susceptibility. Now this is really bad at the bottom. Oh, what are these?
Artery?
Good guess.
Are
Though.
they
Do you see
the
an artery on
ears?
the left? Do you see the artery on the left?
No.
Right, yeah. Somebody said something.
Are they the ears?
Well, it's just above the ears, because if I go down, you can kind of see the ear canal, right? This is the ear canals. So again, air tissue interface. And when you have air tissue interface, you got geometric distortion. The geometric distortion is always so bad here that basically a lot of voxels pile up on top of each other, and then it becomes brighter. They're supposed to be at other places, but because of the geometric distortion, everything that you have over here piles up to here because of the big susceptibility. Okay, so this is called pile up artifact, and that will be true only when it's a spin echo. So spin echo, you don't get the T2 star loss that is typical, but you do get geometric distortion. And so things pile up. If this was a T2, like just a regular echo planar without the spin echo, then basically this was just a hole, like you would use like a black hole, like no signal whatsoever because of so much decay. All right. So that's a fun one. That's diffusion. And the last one that I want to show you is actually arterial spin labeling. Do you remember? Oh, I told you about that. So arterial spin labeling is a sequence that you tag the magnetization in the neck, and then you invert it, and then you wait till it reaches the upper head, and then you image with the inversion, without the inversion, and compare. And that's to image cerebral blood flow to be able to see it. These are the kind of the images that look like, you see how blurred they are? They're very low resolution because you have to image, there's not, you have to wait, you have to excite, and then you have to image very quickly, and then you have to wait a long time, and you have to excite again, wait till the blood comes. So it's a very slow sequence. So what they do is they just do low res. Also, the percent change is about 5%. So it's very, very low. So these is how they look like. But then when they process it, they do some fancy processing to actually extract the cerebral blood flow. And that would be a map. This is a map of the cerebral blood flow. And if somebody would have, for example, disruption of the blood flow, then you would see dark areas that are non-symmetric, for example. You don't want to see my email, do you? Yeah. Okay. So I thought I'll share this with you because that was pretty interesting. Oh, the other thing that people do is they process the diffusion images to compute what we call ABC, apparent diffusion coefficient. So it's a map of the diffusion coefficients that you can actually extract, and this is kind of a map representing the diffusion, coefficients. So lots of diffusion in the CSF, for example. Okay, less diffusion over here, for example. I didn't show you the coronal diffusion, and I have to show you that because it's pretty cool. And the reason it's cool is because it is so corrupted. Look at how the brain is disrupted. Because of the geometry, different areas like my shoulders, the fact that you have shoulders that, there's an edge with respect to the main magnetic field that creates a big distortion of the magnetic field. It's not as bad as you go high up in the brain, but it's really bad at the bottom. You see how the brain is distorted? It's not real. It's just, oh, and the spine, look at the spine. These. This is not the spinal cord. No? Any questions? So I thought that would be fun to show you. So hopefully you've seen some connection also to what you've seen before, and trying to put things together. We'll talk more about that, and as you'll see more about contrast, that's chapter 8. Hopefully, and contrast and imaging, and how you do that. That's my hope, is that you see more clear, and I'll show you more examples of that too. All right, any questions, or can we move on? Nothing? You're so quiet today. I'll sip some coffee till you think of the question. This is really good coffee. I could have made something like taste your choice, but no, I chose to make me some really, really good coffee.
Okay, I have a question. What does HW stand for on this slide?
Slide.
The one that you have up?
Homework.
Oh,
Because yeah, because you have a homework question about that. It's a good question. Yeah. Okay, so you remember that? So that's where we ended last time, and that was a minimum motion artifact adaptation. It's not a trivial adaptation. It's a minimum motion artifact adaptation of a gradient echo into a spin echo, where we added a 180 over here. Oh, don't draw on the slides. When you added a 180 over here, and then the spins refocused at this point, and that's exactly where the gradient echo and the spin echo happen, and so that's where we actually perform the imaging. And we have to flip that thing. What is that thing?
Gradients.
Yeah. Polarity because of the 180. Because the 180 actually, basically reverses whatever you do before that. Okay, so it reverses the phase, so it flips their polarity. Okay, the fact that I have a 180 over here. So then I said something about parasitic, something causes which is not phase encoded and stuff like that, right? So, there's, if you think about actually, echoes that are, signals are being created. Well, there's this one, right? There's a 90 degree, and that 90 degree sees the phase encodes and sees the gradient encode. Okay, and then it sees the refocusing, and then it sees the readout. However, there is a parasitic, like if the 180 is not perfect, then that could actually create some MXY components. And those MXY components actually do not see the phase encodes, right? They only see this readout gradient, right? So for those spins, it's like we're just going from the center of K space and collecting this data. Actually, we're collecting a little bit more because there's no rewinding, right? Okay. That's what's really happens. But the computer on the scanner takes this data, right? For phasing code number 1, we'll take this data and place it in a matrix over here. And then the next phasing code, you take again the data that you collected, and then you place it over here. So a dumb computer will just fill exactly, n times the same data. Okay. And this is just the contribution from this parasitic, right? The contribution coming from, the rest of the echoes or the, or the spins would actually collect the right thing, because those spins will, whatever's been excited over here will then collect, this line and then put the line, in the right place, and then collect this line and put the line in the right place. But in addition to this, they get this data, but it's combined with this, and it's just put in their exact same place. So you got a constant signal for every single phasing code. It's just constant. So if you have a constant signal for every phasing code and you've taken a Fourier transform of it, then what do you get? So it's constant in Y, but it's not constant in X, right?
Projection.
Well, something is constant, right? That's like the it's not changing, right, in the Y direction. So when you take a Fourier transform, then in the Y-axis, it cannot spread out, right? Because it has no change. So in the Y-axis, it's just going to concentrate in the center. Okay, so the image that you get from this is an image of the brain with, well, I'm not using the right colors. Hold on, let me actually use color. So when you go and reconstruct this, then the brain will reconstruct great, but this parasitic signal is just going to be kind of a stripe in the middle of your head, or in the middle of the image, or whatever it is. So that can be distracting, and people don't like that. So instead, what people do is, for the first phasing code, they do a plus 180. And then the second phasing code, they'll do a minus 180. And then the next phasing code, they do plus 180, and so on and so forth. Now, for the red signal, it doesn't matter, because it's going to be refocused no matter what. And so that's not it doesn't change. But the signal that was generated by this excitation, it's like exciting with a plus or exciting with a minus. So their phase of this of this black line, or this black signal, that was over here, would be modulated by being positive and negative, positive and negative, positive and negative, positive and negative, and so on and so forth. Every odd line. Now you have some constant signal that's modulated by plus minus 1. What does it do? What is plus minus 1 modulation?
It should success by half your field of view.
That's right. So half the field of view, so that artifact moves up here. And it doesn't overlap with your image anymore. And you've seen this in the lab now. You'll, I think, get it in the homework this week to actually go and derive it. And then you can kind of see those effects. See? Pretty cool, huh?
I have a question.
Yeah.
All the way back in step 1, why do you get some new spins when you don't have a perfect 180?
Oh, okay. So this excites a slice. The rest of the volume is not excited. Now you apply a 180. That refocuses that slice, but it also inverts the rest of the volume, right? The rest of the volume has a MZ up. Now after this 180 should, this is non-selective, right? So everything would invert it. Now imagine if it's not inverted perfectly, that means that there's still there's some MXY components left from outside of the slice. Here's a volume. I'm exciting this slice, right? Now I'm inverting. Sorry, I'm applying a 180. What does the 180 does? Well, the 180 will refocus this part, but will invert all these guys. Okay, so take a spin from here, from this area, and see what happens to it. That spin was up, right? And then you do the 180, so you know it did this trajectory and went down. Well, what if it wasn't a 180? What it was a 175? So that spin traversed up to here, and now it has an MXY component.
Thank you.
And so this one, all of these have as XY, quite a bit of them. And so all these would produce a signal that would then end up being an artifact. Okay, so here's an issue. This is a slice, this is a simple T2 weighted spin echo, right? You do a 90. By the way, you do a 90X and a 180Y. There's a reason for it, and that's because if you do a 90X and 180X, then if you have an error in the 90 and an error in the 180, those accumulate. If you do a 90X and a 180Y, then those errors don't accumulate as much. So that's one advantage. Definitely, if you keep on doing an extra or more 180s, then those errors will accumulate more and more and more, and that could be a problem. And so this is why often the 180 is orthogonal to the 90 in terms of the axis of rotation. I'm not going to talk about it too much here, but just FYI. So you do a 90, and then you do some phasing code, like pre-winder, phasing coding stuff, and then a 180, and then you read over here, right? This part, because you want it T2 weighted, that would take some tens of milliseconds usually. Maybe 20, 30 milliseconds, 40, something like that. Tens of milliseconds. So there's a lot of dead time over here, right? But the real big dead time is over here, because in order to do T2 weighted, you have to wait till the magnetization recovers completely and then excite again. Because you don't want any T1 weighted, right? Like you have to wait till the magnetization recovers. So for that, you have to, till you repeat the next one, the next phasing code, well, you have to wait a few seconds. Maybe 3 seconds, 4 seconds. Okay, so that is a long time. So now, over 3 seconds, you're spending maybe, what, 8 milliseconds reading? That is a very inefficient acquisition, right? Basically the spins, and then you do it for one slice, and then you do it for another slice, and then you do it for another slice. Whoa, that is super slow. That is the slowest. This is why MR in the 80s was like one of the slowest things that you could ever think of because of this. Okay, just completely inefficient acquisition. And one of the reasons that there's a problem is because, this actually affects all spins in the entire volume because it's non-selective. So what we could do perhaps is make this selective. If we make this selective, then you're not affecting all those spins, and maybe you could do something in, during that dead time. Okay. So in the next slide, what I'm going to do is I'm going to take this part, I'm going to make this selective, and I'm going to take this, and I'm going to do what computer science people do all the time, is they package this and do abstraction. Say, oh, this is a function that does this, and I'm going to have many of these boxes within a single TR. Okay, so that's kind of what I'm going to do. Okay, so here's a 2D spin echo that was inefficient, but we add what's called a multi-slice using the selective 180, and using this approach, we can basically have no time trade-off, but then read all the time and have many, many slices acquired with the same scan time. Okay. So this is how it goes. Let's say this is my volume, my blue volume, because it's full of water. And then I have slice 1, 2, 3, 4, 5, 6, 7, 8. Okay. And remember that box? Each box is a slice selective spin echo. Okay. So I'm going to excite. This is a few tens of milliseconds, right? So I'm going to excite a slice 1, and I'm going to read one phasing code out of slice 1. Okay, then I'm done with slice 1. Well, what I can do now is go and excite slice 3. So I'm going to excite slice 3 and do exactly the same thing and read out the signal from slice 3. And then I'm going to slice 5, slice 7. Now, anybody has an idea why I chose 1, 3, 5, 7, and then 2, 4, 6, 8?
Because their slice select might not be perfect and it might excite other spins.
Just 12 points. Very nice. Yeah, absolutely. So what happens is, first of all, the selectivity, remember, it's with whatever time bandwidth is, right? You pick. So it's, it could affect slice 2. And if I excited slice 2, now it's going to hurt its signal. So if I excite slice 1, 3, 5, 7, by the time I reach to slice 2 again, these spins have time to recover. The other thing is the 180 often needs to be a little bit wider. So even when I choose a 180, it's usually a little bit wider, because I want to have a 180 angle even on the transition. Okay, so that can definitely cause interference between slices. So so this is why the order is 1, 3, 5, 7, 2, 4, 6, 8. Okay. So by the time I reach slice 2, a lot of time involved. Maybe, I don't know, if this is 50 milliseconds, I don't know, like 50, let's say 50, 100, 50, 100, 150, 200 milliseconds. So it's a lot of time for it to recover. Maybe not recover fully, but it's a good. You can put more slices, of course, and that makes it easier. And then after I finish this, then I repeat the second phasing code of slice 1. Second phasing code of slice 3. Second phasing code of slice 5, and so on and so forth. So really, my TR, my time repetition, is this. It doesn't change. Slice 1 doesn't know that I excited slice 3, 5, 7, all that. Like, it just doesn't know. Right? There's no interaction because of slice selectivity. So it just recovers during this time. And then when I hit it again, then it's being excited. But I hit all of those in between. Yeah, pretty sweet deal. So when imaging a slice, basically other slices have time to recover. So it's very efficient. We're always collecting data. The dead time is really very small. So what you see is when you prescribe a spin echo sequence and you prescribe one slice, it will take you, I don't know, 3 minutes to scan. And then you prescribe 2 slices and still 3 minutes. You prescribe 3 slices, still 2 minutes. 4, 5, 6, 7, 16 slices, still 3 minutes. Like, it doesn't cost you because it just puts it in till you reach a point where, there's just not enough. And when that happens, if you don't compromise on the TR, then now your scan time will double, because you'll have to finish slice 1 to 8 first, and then you'll have to do like the next slice, separately. Okay, so you basically what people do then is they set up a TR that's reasonable, and then they squeeze in as many slices as they can, such that it's efficient. And once you see that it overs, then either you don't get more slices or you increase the TR so you can fit more. Okay. Now that's You know, that's a lot of MR. This is like 80%. You know, not 80% of MR in terms of sequences now. Multislice, you know, it's less selective, you know, T2. Yeah, that's a lot of MR there. Cartesian. Now, one thing that we didn't talk about, and I'm just going to throw it right now, is there's a lot of 180s going on, right? So a lot of SAR could be, because like here, think about it, TR, you know, you put some 90, 180, and then you wait for like a few seconds, that's not a problem. But suddenly you're squeezing another 180 here, another 180, another 180, another 90, 90, 180, so now SAR increases. Okay, so that could be also a limitation that would limit the number of slices that you can. And then there's another thing called, or I don't want to talk about. It's related to what's called magnetization transfer. So this is not something that we necessarily going to cover in class, but basically, when you actually put a lot of power, you might actually start interacting with like there is magnetization that's transferred between the water pool and the protein pool, for example. And protein pool have very short T2, and there will be this exchange. And so the more RF you do, you're actually exciting also the spins in the protein pool. And that, because there's exchange with the water pool, that would actually reduce your signal next to protein. So your contrast may actually change when you do multi-slice, even though you don't mean to do that, because of that exchange that happens. And so you have to realize, you know, so there's this effect which is called MT effect in multi-slice spin echo, which could be a problem. And so that can also limit the number of slices that you do. But that's again beyond. Okay, so let's talk about slice selective, actually 180s. So first of all, you can't just take this 90 and scale it up in terms of amplitude, right? This has to be some Schneider-LaRue pulse or some other pulse that creates a nice 180. Okay, so that's one thing. And then this is how it looks like. Now, it doesn't look exactly like you would imagine in terms of the gradients. Right? So in the lab, by the way, you didn't have these. They only had this part. Okay. Which is great. It should still work, except that if you still have a imperfect 180, then you still might create some excitation, you know, parasitic excitation over here. And when you did that in the lab, then you saw some artifact, even though it was actually slice selective, if you don't remember. So in order to mitigate this, we actually add these two blobs. And this is called a horned gradient for some reason, and because it's a gradient, it has like horns on both sides. Okay. Now, this doesn't make sense. This makes sense. This makes sense, right? And this makes sense. These not necessarily make sense. So let's try to track the phase graph of the pathway of whatever's been excited here, where it goes through. And then we'll also track the phase graph of what a parasitic excitation that happens here, what happens to it, like what kind of phase is going to have. All right, so let's do that. And we're going to change this into blue, because it's going to be a blue phase graph for whatever has been parasitally excited. So let's see the 90. So the 90 signal, you excite over here, right? So then it starts at phase 0. And then I'm just going to ignore right now off resonance. I'm just going to consider the gradients in the z direction, just the z direction, as the contribution of phase. Okay. So basically this stays constant, right? Till it reaches this gradient. Okay. What happens when this gradient is on? What happens to the phase? Spins at different z positions will start having different phase, right? Because of this. So I will start having kind of linear, phase accumulating. Okay. Does that make sense? Now, what happens here is quite complex, but I know that after a 180, my phase is inverted. So I'm just gonna ignore this part. This is a don't care region. I don't care what it is here. I don't know. I actually don't know exactly what's going on. But after the 180, my phase is going to be here, negative. Okay. And then this adds a positive phase again versus spins, right? So whatever you have, it's nicely going to be refocused by the end. And so the phase of this echo is going to be refocused at this point. So the fact that I put a positive gradient over here before the 180, for spins after the 180, it counts as negative. And you have a positive gradient here and a positive gradient becomes negative after that. So they cancel. So the effect of this gradient and this gradient cancels for this excitation. It basically does nothing. Completely transparent. So spins go as if these do not exist. Okay, and then you continue on.
Ricky?
Yeah.
On the first 90, did you just skip the step of the phase going up and then down?
Where? Oh, this part?
Yeah.
No. Oh, so after the let's start. Basically, I should have started actually at this point.
Yeah, okay.
You're right. Yeah, absolutely. Yeah, absolutely. You're absolutely right. And I can see that the phase was here pretty much, and then it went down. You're right. Thank you. Okay, so what happens now to the blue? Well, the blue doesn't exist here. Where is it generated? The blue is generated actually here in the middle. Okay. So it's generated over here. And then starts dephasing with this at a slope. And then what happens here? Well, that even dephases it more. And then it stays straight. So pretty much for any parasitic excitation that happens, there's a lot of phase accumulation across it. Hence, it's going to be killed. So this acts as a crusher for whatever is being excited here. But because of that, then everything that is excited before goes through. Ah, what a clever trick. So if we really wanted to teach you slice selective spin echo, we would have actually added these ones. but we wanted you to do the chopping and all that kind of stuff. And if we had more time, we would have let you do a multi-slice spin echo, but we didn't. All right, cool, huh? So if you think that I'm just inventing this, here's actually what we called a fast spin echo or a turbo spin echo or rare. And here's the thing. So every time I apply 180, I get a spin echo, magnetization refocuses, right? And then it dies off with T2 star. Well, nobody says I cannot again refocus another 180 and then acquire, instead of acquiring, you know, the same phasing code, I can actually acquire another phasing code within the same TR. And then I can do that, I don't know, 100 times. And if my spins have a long T2, I will be able to still create an image because they won't decay. So here's the sequence is called Fastspin Echo Rare. That's by Jürgen Hennig, one of the tallest people I've ever seen in MR. Phenomenal sharp person, unbelievably. I mean, this is a legend in the field. And he basically created this fall sequence where you apply a 90x, and then you do a 180 refocus. Okay. So before you do the 180 refocus, you do some pre-phaser, right? And then a 180 refocus, and you see the horn gradient? Yeah. And then you have a phasing code, and then you read one phasing code. And then you rewind that phasing code, and then you do another 180, and then do another phasing code, and then read the second phasing code, and then another 180, and so on and so forth. Whatever comes in here, the result is that you effectively collect one case-based line, another case-based line, another case-based line, another case-based line, another case-based line, and so on and so forth, but extremely rapidly, because this could be about, I don't know, 10 milliseconds. Right? So, or even less, it could be, you know, 5 to 10 milliseconds. So let's say you do 5 milliseconds, and then you do about 100 of them. So it's half a second, and you get a single shot image in half a second. Okay. And that's because, and of course, it's a spin echo, because every time that you cross the center, you know, you get a spin echo, and a spin echo, and a spin echo. And of course, you can imagine how hot that sequence is. Like you can lie in the scanner, and when you do that, then you feel your, like the swarm that happen in your like tummy sometimes. Like you feel the swarmness. I don't know if you ever did this. And the not the pre-scan, the calibrate, like the localizers are often this type of scan, because you want them to be really quick. And so like you go into the scanner, and then suddenly like, ah, it's nice and warm. Ah, it's nice and warm, because of that sequence. So this is rare. Okay. You know, you should call it rare, because this is how Hennig called it, and this is how he decided. And then the manufacturer started calling it either fast spin echo, that's GE, turbo spin echo, Siemens, and I forget what Philips does. Okay.
I have a question.
Yeah.
What's a CPMG? Is it the same thing?
Kind of. CPMG is any sequence which is a 90x, and then 180Y, 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 180Y after that. And it's called CPMG because they realized this accumulation of error. Carl, Purcell, M, I forget, and G, I forget. but I can look it up.
So,
As-
so Henig's thing was to add these.
Yeah,
points
to
in
add
the
phasing codes.
phase.
Yeah, exactly. So
Can you go over it
CPMG
again?
you
Why
would-
do we need those phase again? I missed it.
with this.
Why
No,
do we
hold on.
need these flips?
So you do, if you wanted, let's say, to image the T2 decay of spins, right? Yeah, you do a 90 and then a 180 and a 180 and a 180. And every time you'll get like an FID, and then you could actually fit a T2 like exponential curve to that, right? Okay, but what Jorgen did is instead, he says, you know what, how about the signal decays, but it doesn't decay that much for short, for long T2 components. So let's just ignore that part. And let's put phasing codes in between those 180s, such that in the first 180, we collect, the first line. The second 180, you collect the second line. The third 180, you collect, so on and so forth. And so at the end, instead of actually getting multiple echoes in, for the same phasing code, you actually get a single image. And then you can just reconstruct it. Does that make sense?
I have to think about it.
Because the same magnetization kind of refocuses right again. And so now you can actually encode it again because it's like, it's going to appear. So I can do another gradient echo. And then it appears again. And so I can just, encode it again. And so on and so forth. But I can encode it with different phasing codes. And if I do that, then I create an image. By the way, that can be a fantastic project implementing that, for example, on the aspect scanner.
I have a question.
Yeah.
I was wondering, is it possible to select multiple slices at once to speed up? the
Yeah.
scan?
Oh, yeah. That's called simultaneous multi-slice. And there's good reasons to do that. First of all, the extreme would be to excite the entire 3D.
Right.
Well, the thing is how you separate those slices from each other, right? So you have to do something about it. How to separate.
I was kind of
So-
thinking like you could do it, like a couple slides ago, you showed the multiple slices and how you would line it up. I was just thinking
Yeah.
like slice 1 and slice 3, you just have those going at the same time. And
Right, but their signal, then you would phasing code them exactly the same, and their signal will come up combined. Now, how do you separate then slice 1 and slice 3 from each other?
I'm not sure.
Well, there is possibility. If you, for example, do Z gradient encoding, that's one way. Another way that you could do it is, but this kind of becomes 3D. It will be like 3D with spaces. And then like for example, if you have, let's say I have a volume and I excite actually this slice and I excite this slice in the volume. And the rest is going to be black. And I can now do also phasing coding in the Z direction. So I will get a lot of black and then 2 slices, So then you can think, maybe I don't have to do so much Z phasing coding. Maybe I can do a few of them, right? So yeah, so you could definitely do that. So then they'll alias, but they'll alias over the black parts. So not a problem. But there's other ways. Actually, if you have an array of coils that surrounds your body, some of the coils, these ones will see this slice better than they'll see the bottom slice. And then some others will see the bottom slice better than they'll see the other slice. And that may actually help you separate those. And this is called simultaneous SMS, simultaneous multi-slice. And it's a big thing 5 years ago. A lot of people started putting that, and now it's in products and really, really useful to do EPI, actually multi-slice, like whole brain EPI, sped up significantly using this idea of exciting multiple slices together and then using coil separation in order to speed things up. I'm not talking about that now. Yeah, but absolutely. The other thing that people do, and I didn't talk about this, and I might talk about it later, it's called Hadamard encoding, where you excite, your slice profile is something like that. This is Z. This is slice 1 and this is slice 3, I guess. And then you repeat, and then you make an image, right? So I make an image of this slice and I make an image of this slice, and the result of that image is slice 1 plus slice 3 overlaid on top of each other, right? But then I can also create an RF pulse, which excites slice 1 and slice 3 that way. And then I will get an image which combines slice 1 and minus slice 3. And then when I add these two images together, I will get slice 1. And when I subtract these two, I'll get slice 3. Okay, so it's instead of gradient encoding, you can actually use RF to encode spatial information. And it's called Hadamard because it's a Hadamard basis. 1, 1, 1 minus 1. Oh, that's, but then you could do more than that. Like you can do 4 up to 8. Beyond 8, the amount of power, because the time bandwidth has to increase. So the amount of power you're going to be started depositing is significant. So it's not efficient above 8.
Mickey?
Yep.
Good question. So what's the benefit in doing this over just doing imaging of slice 1 and slice 3? Is it used for SNR?
Separately?
From,
Separately?
yeah.
Yeah. When we talk about SNR, then you realize that if I do, okay, I'll just mention it briefly. So I can image slice 1 and then an image slice 2, right? Separately, right?
Yeah.
So that's exactly the same amount of time that it would take me to image slice 1 and this, and then can somebody stop messing up with my slides, please? And then this one and this one, right? It's exactly the amount of time, same time, right? So the thing is, when you collect this data, you don't collect any information from those spins, right? So if you think of just collecting data, so here is spending half the time collecting data for this slice and half the time collecting this. Actually, this is n equal 1 time, collecting a slice, and this is the same time collecting slice, right? But here I collect information from both slices at the same time. That's n, and then that's another 1. So effectively, I'm observing the same slice twice as much.
Yeah, but
So
what if
there's
sorry.
an SNR gain associated with that?
Yeah, but what if there are some effects that don't cancel in the second
What
slice?
effects?
I don't know. Maybe flow. Maybe it's been moved.
Yeah, get
so-
artifacts like everything.
Yeah.
Yeah, absolutely. You get artifacts.
Okay.
But flow and stuff will affect this one too, right? It's just not,
Well, no. If you only image it once, then no artifacts. Or, I mean,
So there's less chance for it to be affected, right? Like you image this over, let's say this take 5 seconds, and this is 5 seconds, this is 5 seconds, this is 5 seconds. Will you stop, please? Like, why do you want to do that to me? Anyway, each one is this 5 seconds. Then basically, to get, in the second case, you have that 10-second window which you collect information. And if something happens during that 10 seconds, more likely to happen as opposed to 5 seconds each. Yeah. So I agree with you that it could be more sensitive.
okay, thank you.
But the benefits are significant. Actually increases with square root of the number of slices. And we'll talk about that when we talk about SNR.
Thanks.
Okay, so let's talk about other non-idealities in the next 10 minutes or so. So first of all, we assume that the RF is uniform, right? However, guess what? It isn't. necessarily uniform or perfectly uniform. So that has a few consequences. First of all, it would affect your excitation. So let's say you want to do a 90, 180, right? You get 90 degree, when you excite 90, you would get 90 in a lot of places within the volume, but some parts of the volume will have 100 and some parts will have 80. Okay, so it doesn't have to actually be a 90. So that can cause varying flip angle in the volume. Is that a big issue? Could, but not, depends. Like anything that we do. Definitely the 180 can be a big issue, right? We wanted to refocus, right? But now it doesn't fully refocus in all places. So that's going to have signal dependency. If I want to do an inversion, for water to really cross 0 at the right time, well, if it's a 170 and if it's a 160, or if it's a 180, it doesn't cross at the same time. And so now my suppression of water is not going to be as nice. And I'm going to have spatially varying suppression of water. And that could be an issue because suddenly CSF starts showing up in some places. And you might confuse that maybe for, some anatomy. Obviously you won't if you're a radiologist, but if you're not a radiologist, like, oh, what is this bright stuff? And radiologists tell you, oh, this is beyond homogeneity, don't worry about it. Okay. So that could be an issue. Okay, so B1 homogeneity can be definitely. If you want to suppress fat, for example, you want to do a 90 and then crush. Frequency selective 90 on fat, and then put a large gradient. If it's not a 90 exactly, then you have fat left, signal left. And that can also be significant. Okay, so you'll get spatially varying flip angle. You also get spatially varying phase. The phase is actually non-uniform space. Okay, if you have a coil, right? Like if you actually do a bias of our, simulation of a current in a loop, put a current in a loop, right? So you'll see. So now I'm putting the loop in this orientation. So here, the B field actually goes this way. Here, the B field goes this way, and here the B field goes this way. And below, the B field actually goes this way, right? Because you have these field lines that come out, right? So that also means that if I apply an RF excitation using a non-uniform RF excitation, that also has a phase component associated with it. And that's actually one of the sources of phase in an image. I told you that the image should be real, but it isn't. Well, one of the sources of phase is actually this phase varying RF excitation, or space varying RF excitation. And that's why the image is actually not, not real. Well, it's a real image, but it's not real valued. So that could cause problem. For example, I mentioned fat saturation and, flare, inversion, inversion recovery, all that stuff can cause an issue. Actually, it gets really, it's not a huge problem for low fields. It gets really, really bad in high field. And the reason that it gets bad in high field is the wavelength. So what's the wavelength at 1.5 T? So 64 megahertz. If you want to know the wavelength, do 300 divided by 64. That it's kilometers, like the speed of light, it's like approximately 300 and 300,000, something. So divide by 64, how much is it? 5?
4.7 is 5.
Yeah,
Right.
so 4.7 meters, right?
Yeah.
So that's the wavelength. So, it will be pretty uniform across the body, right? So the phase of the RF, because the wavelength is so high, then, you can assume what's called a quasi-static. So the entire body is exactly the same phase, right? And you forgot something. That'll be the wavelength in free space. Our body, though, it's a big blob of water with a dielectric constant that is not of free space. And the speed of light in water is much slower. It's about third. Right? So I think it's third, right? Is it, or 2/3 or something like that? I forget. Anyway, my point is, the wavelength in the body is basically the third of the wavelength. So it's of that. So it's still 1.2 meters or so, right? It's not like or something like that. Maybe 1 meter. Not a problem. What about 3T? Well, 3T now it's like 50 centimeters, right? So now you got a whole wavelength and 50 centimeters. There's some people that are 50 centimeter wide, right? So now it's not quasi-static anymore. What about 7T? That's 300 megahertz. Now, even the head now is not even in a quasi-static regime, right? So that could be this wave effect basically says say that different parts of the volume will see actually a different field because of those wave effects. So that is a problem. The other thing is that RF, this is RF excite, but also RF homogeneity also affects the receive part, because especially if you have local coils, like if I have a volume coil, then it sees the body. It could be perhaps uniform, but often we use arrays of small coils, and each one of those coils are sensitive to a very local area, and so then you got different illumination of the image that comes out. So here's an example of this is a body. It's a sagittal cross section of a body. Anybody knows what is this? It's a T2. T2 looks like very bright T2. What's bright on T2?
Is that bladder?
Yeah, the bladder. That's right. Yeah, it's the bladder. We're super bright on T2. But and this is the liver. And you see what happens? Like you see this dark? That's because the body was so large, such that there's actually a standing wave with a null at this point. So there's actually no RF excitation happening here. So this is an artifact actually. And that happens at 3T. Okay, so you try to excite this homogeneous volume, but then suddenly, oh, wait, nope, you get darkness. So people try to compensate for this in various different ways, and maybe we'll talk about this, but if you want to talk about, you want to do a project on parallel transmit, that's one, or B1 inhomogeneity correction pulses, or B1 measurement, that can also be a project. Okay, implementing a B1, doing a review, during your review on different B1 mapping, for example. This is the B1 excitation field, right? But it also affects receive. So here's Phil Beatty. I don't know if you know Phil Beatty. Phil Beatty is a former lab mate of mine. Did our PhD together. And Phil worked in the area of parallel imaging, so imaging with multiple coils. And now this is a picture, and this is a head coil, and pretty much this is one element of a head coil, and this is another element. and there's another element. And each one of those elements see only part, basically are sensitive to the closest part. Like if you actually do a simulation, try to figure out what like spins, how much current they'll induce, then of course spins that are far away from that loop will produce very small current. Spins that are closer will produce higher EMF, and then they'll appear brighter. So the result of this is if you actually reconstruct an image, let's say from this loop, it would reconstruct kind of the head, but it will be brighter closer to the coil. So as if your loop was, somewhere around here. And this one over here was a loop that is like, closer to that. And this one is loop here. And you can kind of see that these are kind of around the head. And each one illuminates effectively differently. Now, when you get all those images, you can then combine them in an image that doesn't have that weighting of illumination. Okay, and there's actually advantage to that. It turns out that from an SNR point of view, imaging this way is actually much more advantageous than imaging with a uniform volume coil. We'll talk about that. The other thing I actually just want to mention briefly is that there's another consequence. I just want you to look at those two images. Okay. The image above, I can say, it's pretty nice image up to here. And the rest is almost black, right? And this image over here is pretty good, but the rest is black. Okay. Let's say this was the phase encode direction. What would happen if I cut my phase encodes by a factor of 2? I can't hear you, Katie. What would happen if I cut my phase encode by a factor of 2?
Mickey, the question is not so clear, at least to me. What do you mean by cut the phase encode by factor of 2?
Well, okay, to get this entire field of view, I need to have like n phase encodes. But instead, I do n over 2 phase encodes with more spacing. Thank you.
Let's see.
What would happen to the image?
We get artifacts related to the undersampling.
Yeah, you get aliasing.
Hmm.
And I'll get basically pretty much, the image replicated. And then the black stuff will overlap with this. But the black stuff overlaps with this. And then this will overlap with the black stuff. So really, it doesn't affect much. Like my field, it basically narrows my field of view. The fact that the illumination is different, right? What would happen to this image? I will also get, this part of the brain. And then the black stuff would overlap with this. So nothing really. I would be able to actually, reconstruct, I'll reconstruct from each coil, reconstruct an image which has some aliasing. But then I can go and say, you know what, from the first image, I'm going to pick this part. And from the second image, I'm just going to pick this part and then just stitch them together. And now I saved half the scan time and I don't have aliasing. Because each one of them limits the field of view. Does that make sense? And I think you can do similar things with this one and maybe this one in the other direction, right? So you can kind of imagine how actually imaging with multiple coils can actually save you scan time. because they do select, they do have some information about position. Because this coil that's here, only illuminates, this part. And then I have too much stuff here. And only this part is bright for this coil, and this part is bright, right? And this part is bright, and this part is bright. So maybe I could reduce my acquisition time by leveraging that information. This is called parallel imaging, and there's many methods have been developed actually how to do a speed up of acquisition, reducing the number of phasing codes so that you can image faster. So big, huge game, huge. I mean, there isn't a single almost sequence in the clinic right now that doesn't use parallel imaging. The fact that you're imaging with multiple coils, it's almost transparent to you when you actually scan. It just turned on by itself, and then it's just like you type 2x acceleration button, and it speeds up factor 2. So is that a factor 2 a big deal? Well, ask a patient and needs to lie still for, I don't know, 3 minutes. Now they only need to lie still for a minute and a half, for a single scan. So that could be significant. What about if you do a full exam that's supposed to be an hour, now it's half an hour? A factor 2 is really significant. And then can be used for other things. For example, if you do EPI and you want to get a single image, well, it takes you time to go from the top to the bottom. And if it takes you a long time, that means that a lot of distortions, a lot of artifacts and T2 star effects. But if you can go twice as fast because you're skipping lines, then half the distortion and much less T2 star. So suddenly you get also SNR back. Okay, because the signal didn't decay as much. So lots of benefits for that. All right, I think I'm done. That's wonderful. Some of the things that we're also going to talk about next is we're going to talk about, let's say, gradient non-idealities that exist. There's a few of them that we talk about next time. And then we're going to move to chapter 8 after that. Okay, and chapter 8 is all about image contrast. Okay, so, different sequences, how do you do T1, T2 weighting, steady state imaging, and all that fun things. Oh, I forgot. Oh, yeah. So by the end of spring break, we're going to post some suggestions for projects. But by the end of spring break, we will want a paragraph from, you will need to assemble groups. And you could do that through Piazza, I guess. Can we set up a group or something, know how to group up? Okay.
Sure, yeah, we can have
Or
a
sign up
discussion.
sheet or something. We'll have something
Yeah, or some idea. Yeah, okay.
like a Google
Okay.
Doc or something, how to create groups, and then you'll
Mhm.
create groups, and then we'll want you to submit either by the end of spring break or maybe a few days after, a paragraph describing what is your project, and then we're going to review it and then discuss with you whether that is appropriate or not. Or maybe usually students propose over ambitious things and I just make them do less from a realistic point of view. So that's what we're going to do after. And so that will be, and from that then on, you should start working on your projects. Now, with respect to the aspect scanner, it can actually be run in simulation mode. So we're going to try to work over the spring break to get a virtual machine that people can use in order to program. And so that could be challenging because it has MATLAB, I guess. Well, MATLAB and Windows. Two things that are licensed. We'll try to figure out, but if we can't, then we can't.
How big do you want groups?
Okay, what would you think?
I think 2 to 3 people.
Yeah.
Um,
And
two-
one is unacceptable, unless you really can convince me that this is, the only thing you could do. But I don't think we can survive listening to 24 presentations. Okay. Have a nice weekend. Have a nice break. Refresh, come back, stay safe, okay? Bye-bye.